In this lecture, we discuss machine and assembly languages covering chapter 4 of our course book. Looking at our course structure, we see that we have covered chips and logic gates, and also some part of the hardware platform, where we defined the arithmetic unit and the memory units that we will use to build our computer. In this lecture, we discuss machine language and assembly language, which is the abstract representation of the machine language. Okay, the lecture will consist of 4 parts. Part 1 will cover machine languages in general, and we also discuss the hack machine architecture. Then we will discuss the hack machine language instructions in detail. In part 3, the specific issues with symbol handling and input-output handling, and then finally we look at some coding examples. Okay, machine languages in general are real near hardware programming tools where we instruct the computer hardware directly. It also means that different hardware will require different machine languages. Still, a computer hardware typically contains a processor, right? This performs the operations, memory to store the program and the data the program operates on, and registers to store some data temporarily. Okay, data like addresses and data for operation. Okay, so we can say that the machine language is a formalism to manipulate the content of the memory using the processor and the set of the registers. We know that the machine language has to contain binary instructions. Why? Because the inputs, outputs of our hardware chips are binary. Okay, so machine language will use binary notation, but it is very hard to read for us people. So we also have a symbolic notation, and this is called the assembly language. It also means that we will need a translator, right? The translator will turn the assembly code to machine language code. We will call this translator as assembler. Okay, here we can see typical ways of representing instructions in assembly. This first one is rather general in real assembly languages. In hack machine, we will use a simple formulation that is easier to understand. What kind of commands or instructions our machine language will contain? Well, we need arithmetic and logic operations like addition, subtraction, Boolean operations. These will be operations that our hardware is able to perform. Then we need instructions for memory access to move data between registers and memory, and for program flow control. We will have simple program flow control instructions like jump and conditional jump, and higher level languages will use these to realize some more complicated flow control. Okay, since there are many different machine or assembly languages depending on the computer architecture, we can have some classification of those together with the computer architecture. Most important ones are the complex instruction set architectures and languages, and the reduced instruction set computers and languages. They differ in the set of instructions they use. In complex instruction set architectures, there is a large set of instructions. It also requires complicated hardware, but it results in very short codes. In contrast, in RISC computers, the instruction set is small, the hardware is simple, but codes are usually long. We also have some new variants like minimal instruction set architectures for embedded systems and special purpose processors, or very long instruction word architectures for parallel processing. We can also classify machine languages depending on the number of operands an instruction can contain. What we build here in this course is a half-address machine. We will see that 2 instructions will be needed for a memory access. Then there are 1-address machines and up to 3-address machines for 32-bit computers. Let's have a look at our hack computer architecture. We design a 16-bit machine. Right, already in the previous lectures we designed 16-bit chips for arithmetic unit for memory, so we will use these to build our hardware. The computer will contain a data memory, a random access memory, the instruction memory, which is a read-only memory, again addressable sequence of registers, registers D and A, and a virtual register M, where M stands for the contain of the random access memory at address A. We need a processing unit or arithmetic and logical unit, a program counter that keeps track on which one the next instruction will be. Then we need a control framework, right, that actually tells the computer what to do. This control will be instructed by the instruction read from the read-only memory. Okay, finally, our computer will contain some input-output devices, specifically a memory mapped screen and a keyboard. So, looking at these units one by one, the memory will contain the data memory, the random access memory, and the instruction memory. Both of them are blocks of 16-bit registers, and both of them will be addressed by 15 bits. We will need 1 bit to note that actually this is an address. The ROM will be preloaded by a program starting at address 0. Okay, the two 16-bit registers, the D register and the A register. The D register can contain data values. The A register will be used both for addressing and to store data. Arithmetic unit will be the one actually that we designed in the previous projects. Okay, some words about our addressing challenge. As we said, we design a 16-bit machine, which means that all instructions has to be 16-bit long. However, we have 15-bit addresses. It means that we cannot pack an operation and an address into the same instruction. Okay, so to address the instruction memory, we will need to load the ROM address into the A register, and similarly to address the data memory through this virtual register M, we will need to load the RAM address into the A register. Okay, so please note already here that the content of the A register, or the interpretation of the content in the A register, will depend on the subsequent instruction. Okay, this ends the first part of the video.